Hello, and welcome everyone to the next event in our webinar series, a presentation by Thorlabs physical optics engineer, Matt Singer. My name is Ryan Priori, and I will be moderating today's talk. Matt obtained his Bachelor of Science and Master's of Science in Electrical Engineering with a focus in nanophotonics from the University of Buffalo, SUNY, in 2016 and 2017, respectively. Currently, Matt focuses on research and development of nanophotonic and plasmonic technologies to bridge the gap between academia and industry. Throughout Matt's talk, feel free to submit any questions you have using the Q&A tool. He will be answering any questions at the end. Now, I'd like to hand off the talk to Matt.
Thank you very much for the lovely introduction, Ryan. So good morning, good afternoon, good evening, wherever you are in the world watching this. And yeah, today I'm going to be discussing the Surface Enhanced Raman Spectroscopy, or SERS, substrates that Thorlabs has developed. So to start off, I want to say that I've been working with SERS, plasmonic biosensors, these types of technologies for quite some time now. And when I was in grad school, I actually used to make my own SERS substrates. And I'm curious how many of you out there make your own SERS substrates, or maybe you buy them commercially. I'm going to put up a little poll to go over and maybe get some feedback on that. But the reason why I ask is because I remember what the struggle was like to make these in more of a research level environment. There's a lot of different aspects that go into making a SERS substrate. Generally, you start off with a design process. This can be done using FDTD or FEM simulations. And in these design environments, you can make an extremely sensitive and perfect SERS substrate. But then the next step is you have to fabricate it. And generally, to fabricate these, you have to go into a clean room environment. There's a lot of preparation for the substrate that you need to do. There is metal depositions, there is lithography, all of these different processes to create this perfect substrate that you've designed in your software. But then after that, you have to characterize it. You have to understand, did the thing that you made actually achieve the specifications you set forth in your design software? So this may involve some type of SEM imaging. This may involve some type of absorption measurements. And then eventually you have to coat some molecules onto these surfaces and see how the Raman performance is. Now, during this process of design, fabrication, and characterization, the common specs that you're looking to achieve are a balance of sensitivity, repeatability, and availability. So throughout this talk, I'm going to be discussing some of these characteristics and how we met them. And I've actually attached a link down below that is a source that goes over some more specific numbers to these sensitivity, repeatability, and availability metrics. And it's a really good source to help you understand what makes a commercially viable SERS substrate. So with that, let's go a little bit into what I'll be discussing today. I'm going to start off with a little bit of background on Raman spectroscopy. Then I'll get into some background on our nano-textured anti-reflective optics. And after that, I'll introduce an interesting field of physics known as plasmonics. And you'll see how plasmonics and our textured optics can be combined to create our SERS substrates. After that, I'll get into a little bit of the design, manufacture, and very importantly, the characterization of our SERS substrates. And I'll end with some really exciting applications that we've seen customers and collaborators use our substrates for, and hopefully give you some ideas of how you can implement these into your systems, or if these SERS substrates could be a good option for you and your team. So what is Raman spectroscopy? Well, spectroscopy is just the study of how light interacts with materials to identify and understand what those materials are made up of. And Raman spectroscopy really relies on a process known as Raman scattering, which is, very simply put, an inelastic scattering process based on the molecular vibrations that these molecules or materials are made up of. So in this case, you may send in a single wavelength of light into a material that you don't know the makeup of. And based on how those molecules in that material vibrate, they can send off new wavelengths of light to your detector. Now, what's interesting is the amount of light that actually goes through this Raman scattering process or this Raman shift process is very low compared to the incident light you put into the system. Generally, only around 1 in a million photons go through this Raman shift or Raman scattering process. Sorry about that. So what's very useful about this technique, like I just mentioned, is that each molecule can be thought of as having a unique fingerprint based on the light that you scatter off of that material. So this means that Raman spectroscopy or Raman scattering is a very useful technique for sensing unknown materials. So a question you might have is, well, how do we probe this very low signal to obtain this very useful information? Well, there's a few ways. I'm going to discuss a couple of them. But one way that Thorlabs has come up with is the development of our coded aperture Raman spectrometer. Specifically in our RSB and RASP series spectrometers, we use something called a coded aperture, and this is based on a pseudo-Hadamard mask. If you would like to learn more about what that type of Hadamard mask is, I've linked another source below for you to take a look at. But the idea here is that in spectroscopy systems, there's a general trade-off between resolution and throughput. In pretty much all spectrometers, you have an entrance aperture or an entrance slit, and the thinner and smaller you make that slit, the better resolution you can get. However, you're preventing a lot of light from being put through the system. However, if you widen that aperture or that slit, you can experience larger throughput, but you'll have much worse resolution. The coded aperture series spectrometers use a combination of slits that are very small to allow the best of both worlds, to allow large light throughput with high resolution, and software on the back end will actually deconstruct it, or I should say reconstruct that spectra based on all of these series of slits. So currently, we sell two different types of these Raman spectrometers. The first is our RSB system. This is a very modular system. If you want to build your own optical setup with other components or systems that you would like to integrate into it, it can take reflective measurements, it can take cuvette measurements for liquid samples, and you can even output fiber probes to your sample. Additionally, we sell our RASP series spectrometer. This spectrometer has a dual excitation wavelengths, so 785 nanometers for the fingerprint region and 680 nanometers for the high frequency region. But what's interesting about this spectrometer is that there are some built-in and also customly available databases for spectral matching. If you'll remember in the previous slide, I mentioned how each material has its own fingerprint, or each molecule has its own fingerprint. So you can upload many of these known fingerprints, and based on an unknown sample that you place in the spectrometer, you can get a best match of what that material may be. And one last thing I would like to mention is that the SERS substrates that I'll be talking about in the later slides, they will actually work in any company's Raman spectrometer, so don't feel the need to have to buy ours. We just like ours a lot because it solves this throughput and resolution balance. But we have found that our substrates do work in many different companies' spectrometers. So we've discussed this throughput and resolution balance. Again, Raman is this rare process, so we can increase our throughput using this coded aperture. But what are some other ways we can increase throughput? And to go over that, let's discuss anti-reflection coatings. So generally, most optical materials like glass, for use in lenses and windows and gratings, they are going to have some inherent reflection based on them. We generally think of them as transparent. However, due to an abrupt change in refractive index from your background medium, like air, to your optical substrate material, like glass, this abrupt change will cause some stray reflections. So in a Raman spectroscopy system, you may have this very rare Raman process, and now some of it is being lost to stray reflections. So that's not a good thing. So how do we solve this? Well, a very mature technology is based on thin film interference coatings. These coatings are based on dissimilar materials being stacked onto your optical substrate, generally in quarter wavelength thicknesses, and that will create a destructive interference condition on the reflected light. Now, while these are a very mature technology, these thin film interference coatings, they're not without their downsides. Specifically, they are relatively narrowband in performance, and they also are highly angular sensitive. They have high angular sensitivity, excuse me. And this is due to that quarter wavelength condition needing to be maintained. Additionally, for higher laser energy and power applications, these thin film interference coatings are very prone to damage just because of these dissimilar materials being stacked. So how do we solve this problem? Well, believe it or not, Thorlabs has come up with another solution. This is our textured anti-reflective optics. Currently, we fabricate these in UV fused silica glass, and we use an etching process to create sub-wavelength textured pillars. Now, these sub-wavelength pillars allow for a gradual change in refractive index. As opposed to the abrupt change in standard optical substrates, this gradual change can reduce Fresnel reflections down to less than 0.25% per surface, and this is over a much larger bandwidth as well. So you can see here, specifically in the bottom right, the reflection over wavelength, and our textured substrates are extremely broadband performance, and they do have that lower angular sensitivity. This is because they are not relying on a quarter wavelength condition needing to be maintained. Additionally, because these pillars are etched directly into the UV fused silica, they could withstand much higher laser damage thresholds. So currently, we manufacture these in flat windows, gas cells, and we actually just released our textured lenses a couple weeks ago, so that's very exciting. But we are looking to texture many other components, such as fiber end caps, cover slips, and whatever other components customers may recommend to us. And I want to show some really fun pictures. You can see here the textured versus untextured components in our lenses specifically. The textured components really do look invisible, and this is a testament to how well the anti-reflective properties are being developed in this case. So how can we use this technology in a new way? We've developed this method to create very nice nanostructures on a glass surface. So to use these in a Raman application, a Surface Enhanced Raman application, I want to introduce a field of physics known as plasmonics. So plasmons, they're collective oscillations of electron density waves. And there are a few different types of plasmons that people may talk about, or different ways to excite them. The first is surface plasmon polaritons. This is when light of a correct momentum condition is incident on a metal dielectric interface. And if the engineering of these structures and these interfaces are correct, you can very efficiently couple that light to that surface and couple it to a plasmon. So in this case, you're converting this light energy to this collective oscillation of electron density waves that propagate along that interface. Another type of plasmon that you can excite or generate is a localized surface plasmon resonance. This is when you have a metallic nanoparticle, and again, with some careful engineering and design, you can very efficiently couple light to these nanoparticles. Now, when plasmons are oscillating inside of a nanoparticle, they're confined to this very localized area. And therefore, you can see some electric field start to leak outside of the particles. Now, if you have a situation where maybe you have many of these particles, 2, 3, a large number of them, and you start bringing them closer together, you can get something called gap-enhanced plasmon modes. This is where the electric fields of the individual particles begin to overlap with each other. Now, when these fields overlap, they don't just add together, they scale to the 4th power, and you can create this extremely strong, localized electric field. Now, if a molecule that you're interested in sensing happens to fall within that field, because of that high electric field strength, you can actually get an increased probability of Raman scattering. So it's no longer 1 in a million photons. You are increasing that probability significantly. So when we talk about SERS, or the Surface Enhanced Raman Spectroscopy, it's really these metal features that are the surface enhancement aspect of SERS. Now, plasmonics is a really useful field for biosensing, and this has been well studied for many many decades now. And there are a few different ways you can use plasmonics to sense materials. The first is surface plasmon resonance sensors. This is where, for example, you can shine light and couple it through a prism onto a gold film. The prism is used to meet the momentum condition needed to excite plasmons. And as you change the incident angle of that light, you'll notice that the light that's reflected all of a sudden drops very significantly. And at that angle where that reflection drops, you are actually absorbing that light, and you are coupling that light to surface plasmon polaritons along the surface of that gold film. Now, if you were to bind some molecules that you're interested in sensing to the gold surface, you're now changing the localized refractive index, and therefore the angle that your surface plasmon polariton couples will change. And you can use this type of scheme to perform some biosensing. So this is a really interesting way to use plasmonics again, but we're talking about SERS today. So with SERS, like I mentioned previously, you generally have these nanoparticles, and your molecule will hopefully fall within that strong electric field region to get a higher increase in your Raman signal. And there are some very clever ways that people have developed to engineer these nanostructures to get extremely high field strengths over the past decades again. However, there's still a problem where you have to ensure that your molecule falls within that very small region, or you have to hope it does. And this leads to one of the problems that we see in SERS, which is repeatability. Generally, there are SERS substrates out there that can perform very well in one area, but if you move over a couple millimeters, it may not perform as well. And these are due to these hotspots not being very uniformly distributed. So the thought we had was, what if we use our textured substrates and coated them in some gold to create these plasmonic nanostructures? And in this case, we can create a textured SERS substrate. Now, the theory of how this may work is that you have some incident light onto your sample, and you can excite some surface plasmon polaritons along the height of the pillar. Now, because these pillars are relatively thin, you can get these gap-enhanced plasmon modes, leading to this broadband absorption of light. And this would allow for this electric field enhancement to be along the entire height of the pillar, or envelop the entire pillar, as opposed to being extremely localized. This theory was developed using some FDTD simulation tools. So we decided to run some more simulations. And what we found is that this is, in fact, a broadband absorber. The simulations that we've run, we had to simplify them to a single nanopillar, even though, and this was just due to computational efficiency. But what's interesting is that if we look at the frequency domain for different wavelengths of light that are common to Raman excitation, you can see that the electric field is being localized to different heights along the pillar, indicating that there is some credence to this theory. And we're having this broadband light trapping. We are creating this electric field that can be distributed along different heights of the pillar and create this broadband absorption. So in this case, some of you may be asking, is the texturing actually improving the performance, or is it just surface roughness? This was a question I've gotten a few times, and that's because some of the original SERS substrates that were developed decades ago were actually based on just roughened metal surfaces. So to understand this point a little bit more, we ran an experiment where we compared a bare piece of glass to a gold-coated piece of glass, and then a gold-coated piece of glass that it has been textured previously. And what we did find is that only the gold-coated textured substrates produced a good Raman signature, a good SERS signal. And one thing I would like to mention is that throughout the rest of this talk, we used BPE molecules for a lot of our testing. These are just a common molecule used for Raman standardization testing. And what you're seeing in these plots here, these peaks, they're actually associated with the chemical bonds in this BPE molecule. So for example, some of these peaks are associated with these nitrogen rings breathing in and out or vibrating. Some of them are associated with the kind of the central point of vibrating in different ways. So again, these signatures that you're seeing in the graph here are the fingerprint of these BPE molecules. So I just wanted to bring that up because we will be using those moving forward. So now that we have determined that we have a nice structure on our hands in the design phase, we have to manufacture it. We have to fabricate it. Now, being an industry, we like to do things to scale so we can meet that availability requirement of SERS substrates. And in this case, we use 4-inch quartz wafers. We'll take that wafer and we'll texture it. Then we coat it in some gold, and then we can dice them into individual chips for sale. And this is really where the characterization begins, because we need to ensure that the manufacturing process is consistent and uniform across the entire wafer and from batch to batch, from wafer to wafer. So to do that, we developed this metrology set of steps where we take our quartz wafer in, and we have to check the flatness and the scratch dig specifications on that wafer to ensure that it's going to be pristine across the entire surface. We then texture the wafer, and we will measure the reflectivity across the entire wafer. Now, this is to ensure that the texturing was not only done correctly, but uniformly across the entire wafer. Next, we deposit some gold, and we will check the transmission to ensure that the gold thickness is not only correct, but uniform. Finally, we dice them into individual substrates, and we will pull a few witness samples, coat them in some molecules, and run a Raman test to ensure that the Raman performance is meeting specification we've set forth and is uniform across the entire wafer again. So you might be wondering, how do we measure all of these characteristics across an entire wafer? Well, we have developed an automated characterization setup. In this case, we use a 785 nanometer laser driver. We use our RSB1 kit for reflective Raman spectroscopy, and we use a computer-controlled XY stage for these successive measurements. These all talk together in LabVIEW programs, and we can use this to place an entire 4-inch wafer into the setup and successively measure point by point across that entire wafer to ensure that we get a uniform response. So how do we measure this uniformity? What metrics do we use? Well, this is actually highly dependent on how you coat the molecules onto your surface. So in this case, I want to remind people that a common issue with SERS substrates is that they can have a high variance or a high relative standard deviation. Now, some common methods of applying your molecules to a SERS substrate could be micropipetting. In this case, you take a fixed volume of your molecules and you place a drop on the surface. And when we do that to our wafer and we measure across the entire wafer, we see that there are some coffee ring effects, there's some overlapping of droplets, and overall you get this very ununiform coating across the entire surface. And when we measure the relative standard deviation of those areas, we see that the RSD value is around 30%. So this is not really acceptable for many applications. However, if we perform something called a dip coating procedure, where we take the entire wafer and we submerge it in a bath of these molecules, we can then let it incubate and let the molecules bind to the surface and rinse away any excess molecules. We can then take our measurements again across the entire wafer, and we see a much more uniform response. Our relative standard deviation dropped to around 16%, which is quite good for these SERS substrates. So now that we have characterized our uniformity on the wafer scale, we do need to dice them into substrates. So how do we pick what size substrates? That seems to be a common issue with different substrates out there. How big should they be? So in this case, we ran some tests to see how dice size may influence the performance of these SERS substrates. So a thought experiment we ran was that if you have a customer who is micropipetting the droplets onto a surface of a SERS substrate, if you have a fixed volume of molecules and you place it onto a smaller area, you would get a higher signal. If you think about it, if you place the fixed droplet size on a larger area, those molecules are going to spread out more and they will kind of self-dilute across that surface. So we diced some different sized chips, and we found that, in fact, the 3 mm squared chips did have the best performance. However, we found that 3 mm squared chips were surprisingly difficult to handle. They would often slip out of your tweezers and move around on your stage because they're so small. So we decided that 4.5 mm squared was a really nice balance between performance and handling for the size of these substrates. Now, another thing we have to characterize is, now that we've diced these substrates, how do we get them to customers in a good condition? And this is where we have to characterize our packaging solution. So in this case, we have all of these nanostructures on the surface, and they can very easily be damaged. So the packaging can't actually come in contact with the surface at all. So what we found is gelatin pill capsules were a really nice solution to this problem. The pill capsules are rounded on every single edge, and as an added bonus, they are made of gelatin, so they're biodegradable, which is in line with our sustainability initiatives. So to test this packaging solution, we did a durability test. So in this case, we placed chips in the capsules and then placed the capsules in a paint shaker. We would then shake the packaging for some time to simulate maybe a bumpy road, maybe someone drops a box somewhere along the line, to see if these chips would perform the same. And through this durability testing, we did find that there was no degradation in performance, even after this vigorous shaking. So now that we have hopefully characterized all the ways that the chip can get to the customer, we need to take some customer use cases into account. So for this, we ran some linearity characterizations. It is not uncommon when you are doing Raman or SERS testing that maybe the laser power varies a little bit from day to day. Maybe someone changes some of the software settings and changes the integration time. So for this, we want to make sure that our substrates can easily be scaled to some known reference. And in this case, we varied the exposure time and fixed the power, and also varied the power and fixed the exposure time. And we did find that there was a linear relation no matter what the power or the exposure time is. So this is really nice for certain applications where maybe those variables aren't consistent, and you could always scale them to a known benchmark. The next characterization we ran was backside measurements. There are some applications where the excitation laser and the collection optics can't be in the same space as the active SERS area. And I'll talk about one of those in our application section. But what was nice about this test is our RASP2 Raman spectrometer has this very setup. The excitation laser and the collection optics are hidden behind a window, and you have to place your SERS substrate on top of a sample window. So in this case, we ran some tests, and when we found what we found was that even when we account for the thickness of the glass substrate, we can still maintain 80% of the signal intensity compared to a front side measurement. So for some applications, this is a very useful method to perform mirror sensing. The last characterization we ran was for concentration measurements, or limit of detection. So in this case, we used BPE again, and we went to smaller and smaller concentrations down to around 100 nanomolars. That's equivalent to around 5.7 parts per billion. And you can see here that even at the 100 nanomolars, we still see the characteristic peaks of the BPE molecule, indicating that our limit of detection can be somewhere in that parts per billion range. Now, this corresponds to a calculated enhancement factor of around 10 to the fifth. However, I do want to mention that enhancement factor is not always a reliable metric. I've actually linked another paper down below that goes over how enhancement factor can change depending on the molecules you're using, depending on the orientation that they fall onto the surface of your substrate, depending on how you estimate the number of molecules that are on your surface. So while many people would like to know enhancement factor, we feel this is a not reliable metric. So now that we have discussed all of these characterization methods, let's get into some fun applications that our customers and collaborators have been doing. So recently, we've been working with a life science startup who is using SERS to perform urinalysis for cancer detection. Now, this customer is really, they're focused on having a SERS substrate that is repeatable and available. And the reason is they may need 10 to 20 different substrates per patient, and there may be dozens of patients per trial. So in this case, they may need hundreds of substrates in a given order that are consistent and that they can make sure that they have a baseline understanding of what that signal is going to look like. And our substrates happen to be a really nice solution for this startup. We've also been working with a professor at San Francisco State University who is doing photocatalytic monitoring using SERS. So in this case, the professor has some photocatalytic cell, and they are using it to produce hydrogen gas, and they have this closed system. So they can't actually fit their laser and their detector inside of this cell. And this is where the backside measurement capability of our SERS substrates was very useful to this professor. Another area that people don't often think of SERS being used in is art preservation. We've been working with the Metropolitan Museum of Art to use SERS for pigment and dye identification. This is very useful because sometimes a museum may receive a painting and they want to understand if it's real or fake. So they can test the dyes and pigments, ensure that they are of the correct time period. And additionally, if you want to preserve art, maybe some art was damaged, you can ensure that the correct pigment is being used to restore that piece of art. Now, the graphs on the right here are of some different dye molecules that were, these measurements were taken in our Munich office. And you'll notice that these molecules are much more complex than our BPE molecules. But you'll also notice that the concentrations of these molecules are much higher. And the reason for these levels of sensing is because that is common concentration levels in this art preservation field. They don't need to go down to nanomolars or parts per billion concentration often. So these are some really nice results for this group. The next startup we've been working with is a biological monitoring startup who is measuring cyanobacteria concentrations in ocean life. So this startup actually goes onto the boat with fisheries who are catching fish and mussels and clams and all these different sea life for food production. And in real time, they can actually take a SERS measurement and determine are there acceptable or unacceptable levels of this bacteria in the ocean life for food production. And finally, we've been working with a biosensing startup who is looking to do SERS in the Mars rover for life in space detection. Now, this customer was really interested in something I haven't talked about yet, which is lifetime of our substrates. You'd have to imagine if you're putting a SERS substrate on a rocket and sending it off to Mars, it could be many months to many years before it's actually used. So we need to ensure that the lifetime of these SERS substrates is very long. And in this case, we found that our SERS substrates last for over a year and a half. Now, this number is just because we've only been making them for around a year and a half in our R&D environment. We predict that they can last longer, but we're not going to put a number on that quite yet until we've fully characterized it, of course. So with that, I'll leave you all with some closing thoughts. I want to give an extra special thanks to our team in South Carolina, as they're the ones who developed our textured windows, our textured lenses. And it was these textured products and this robust fabrication method that they've developed for creating these nanostructures that inspired the SERS substrates. And what I want you all to take away from this is that for a commercially viable and available chip, a balance of sensitivity, repeatability, and availability is extremely important. And you need some very in-depth characterization and accounting for many customer use cases to ensure that those characteristics can be met. So if you or any colleagues you know are working with SERS, please feel free to reach out. We'd love to learn about the variety of applications these are being used in. And with that, I will quickly thank Longfei, Ryan, Robert, and Jason in our South Carolina team, Eric in Munich, David, Bill in New Jersey, and Garrett in California. So with that, I'll take any questions. Thank you.
Thank you, Matt, for that informative presentation. I've already got a couple questions that I see that have come in, and I'd like to invite you to continue to submit those questions while we go through the ones that we have in queue. So, Matt, maybe you can talk a little bit about um, what's, do we offer these in custom sizes, or can we offer them in custom sizes? I think what I'll restate right now is those are 4.5 millimeter by 4.5 millimeter squares right now. We sell those for $45 per substrate, or a 5-pack for $200. Can we do any custom sizes? Are we offering anything like that?
Yeah, great question. So currently, we, like Brian mentioned, we sell them in these 4.5 by 4.5 millimeters. However, we are open to other sizes. We've had people come up to us and ask, "Hey, can you make these 1 millimeter squared? Can you make them 1-inch rounds?" Many different sizes have been suggested to us. So if you're looking for these custom sizes, please feel free to reach out, and we can find a solution for you.
Matt, can we reuse these, or can you clean these once you've deposited your sample on them?
Yeah, great question. So unfortunately, we cannot clean these. I would say if a customer buys them and they want to attempt a cleaning process, you are more than welcome to. We would love to hear the feedback for how these can efficiently be cleaned. The reason is that certain molecules will bind very, very strongly to the gold surface where others won't. And depending on those molecules and the cleaning method that you use, it may strip away the gold, it may strip away the molecules, it may functionalize the surface in some other way. So we cannot guarantee that the performance would be maintained if you attempt to clean them.
Thank you. I actually see some ones that were coming in right as you were answering that, which was that exact question. Matt, maybe talk a little bit about why 785 nanometer as a laser wavelength for the Raman that we're doing. And then an extension on that is, can we use these for other popular Raman laser wavelengths, 532, et cetera, et cetera?
Yeah, absolutely. So the reason why we chose 785 nanometers is multifaceted. So 785 nanometers is a pretty common excitation wavelength for Raman spectroscopy. This is purely to reduce the fluorescence background that you may see in a system with shorter wavelength excitation. But another main reason is because of the SERS active metals that are common in the literature and in industry. Gold is one of those metals that does not oxidize. It can be pristine for a very long time. So for different excitation wavelengths like 532, silver is often used. However, silver can tarnish and oxidize over time. So we started with 785 for that reason. I will say we are looking into alternative metals for different excitation wavelengths. Specifically a 532 nanometer offering, and possibly something in the more UV Raman area, maybe let's say 405 and below. So there are some metals we're looking into for that.
I think, so you asked a question earlier, Matt, and I think just in watching your slides, maybe it would be helpful to go back again. If you can pull up slide 15, and I'll ask the question. So can you comment a little bit on the surface states that were created by the pillars? There must be some increased absorption, but at shorter wavelengths. Maybe it'd be helpful again just to kind of summarize this slide again based on some of the modeling.
Yeah, so for this modeling, we did have to simplify it just due to computational constraints. So in this case, we have a single nanopillar, and we optimized the height and the width of the pillar, as well as the gold thickness based on our experimentation. And when we did optimize that size, we found that this was really optimized for field enhancement in the 785 nanometer region. So in this case, we were modeling around 10 to the 4th electric field strength for 785 nanometers. However, this value will change depending on the wavelength that's chosen. But you're right, so this is a broadband absorbing structure, and in theory, it can work at other Raman excitation wavelengths. We do have one collaborator who said that he was getting really nice results at 660 nanometer excitation as well. But the idea here is that this broadband absorber can work at multiple wavelengths. However, the kind of surface plasmon resonance of gold drops off significantly as you get shorter in wavelengths. So this may not be as effective at 532 or other shorter wavelengths like that. Does that answer the question?
Yeah, I think so. Thank you. And I know you talked a little bit about the 785 and the transition to other metals. And there would be a rinse and repeat sort of comparison, if you're looking at that performance as you would change your metal. Can you talk a little bit about your modeling tools?
Yeah, so I use numerical FDTD solvers. This is a really nice software for running kind of these, Maxwell equation, based simulations to understand how light is going to interact with these nanoscale structures. So the tools, people have used, I've seen COMSOL, I've seen Tidy3D, I've seen other tools out there. They can all get you the same results, if you use them correctly. But I personally use numerical.
So there's a couple questions that fall within a theme, so I'll try to walk through those. And I think the first one is, if someone wanted to try to do a head-to-head comparison, maybe they have a particular substrate they're using right now and they want to compare it to our version, or maybe just a third party. Are there specific, molecules that you could recommend, or at least on the chemistry side, are there things that you recommend using? I'll give a brief, my just feedback from experience over the years, and then Matt, if you'd like to add on to that, feel free to do so. I think a challenge with that is you get into the application-specific nature of where folks are using these tools today for the research that they're performing. Some substrates, based on whether it's the metal and whether it's the surface binding, maybe it's the features, maybe it's the, how that specific mode or functional group is being enhanced with the substrate. That may vary from small molecules to large molecules. So I think, it's kind of based on your research, if you're in sort of the bio side, you may have a preference to use, a bovine serum albumin, so like a BSA. If you're working on something that's more of a general comparison, you may come back to, work that we did with BPE, or rhodamine 6G, crystal violet, other dyes, tend to be things that you'll see in the literature. So I think it's kind of an application-specific question, and then once again, based on the wavelength that you're working with. Sometimes keeping into consideration the materials themselves. If it's a gold-based metal, then thiol groups, are preferred, for a gold substrate compared to others. So I know it's a very roundabout answer, but I think it's a challenging question. But I don't know if there's anything else you wanted to add to that as well.
Yeah, no, not really. I mean, so I will say I am by no means a chemistry or biology expert. So Ryan will definitely give a better answer than I can. But one thing I found, so a couple weeks ago, I attended the SciEx conference, which goes over a lot of cutting edge spectroscopy research. And one of the things I noticed there is that, there's a common push to use these new sets of biomarkers and analytes to do the SERS sensing. If you look in a lot of the literature, R6G, BPE, those are very common. However, there is a big push to use more complex, functionalized, chemical solutions. So, I can't speak to any of the specifics of those, unfortunately, but there is this push to move away from kind of more simple individual molecules to maybe stacking different layers of molecules to do a type of specific sensing to trap certain molecules onto that surface. So the short answer is that, unfortunately, there really are no common, molecules. As long as you're using the same molecule for all of your testing, it should be a one-to-one comparison.
So, follow-up question with that. Can you comment on how our products have compared to maybe some of the other vendor options that are out there today?
Yeah. So I won't name any specifics just because unless there was a representative here to defend themselves, I think that's unfair. But I will say that there are some substrates commercially available out there that have maybe beaten us in sensitivity, but don't seem to be very repeatable. There are some other substrates that are maybe cheaper than ours, but they aren't as sensitive. So, the commercial landscape out there of, chips you could buy off the shelf does vary in, all these different performance areas in terms of price, sensitivity, repeatability. So yeah, I think that's all I feel comfortable saying. I don't want to disparage any other company or call them out or anything.
So there's some questions here about the how we make them, the things I think that we're not going to go into too much detail on, the specific recipes and details with that. So unfortunately, we're not gonna go into detail there. I think another question that comes up is you mentioned the pill containers. Are there any cross-contamination concerns, or have we seen any observable signal from the container media itself?
So far we haven't. Again, we have been doing some longevity testing. So when we package these, maybe over time there is some outgassing of the packaging or some kind of contaminant that can get onto the surface. In the, I'm going to call it around a year that we've been testing the current SERS recipe with the packaging solution and all of these things, we haven't noticed any discernible background signal.
Yep. I just said I was going to answer things about the details of it, but a question just related to how do you coat the metal particles? Just to be clear, there's a metal surface, so it's, I think, compared to one of the distinctions here, there's colloids, there's types of SERS that you can introduce into a fluid and then look at the sample that way. This is a fixed substrate, right? And that's what we offer today. There's a question here as well. Do you know any commercially sold products that integrate SERS into the product themselves? Matt, I'll let you comment on that, but maybe more importantly, some of our thoughts on where we think this could potentially go in the future.
Yeah, absolutely. So currently right now on the market, I don't know of any integrated SERS into a microscope-based system or something like that. I've seen SERS substrates that are mounted onto a glass slide for a little bit more conformal form factor. So that's one option that I've seen. But yeah, I haven't seen any commercial integration of SERS into an existing tool. My guess is that's because you need to, most SERS substrates are disposable. They're kind of a one-time use, so they need to, be replaced each time. As far as we go into integrating these, mounting these SERS substrates onto a microscope slide is in our very near-term roadmap for new products in this area. But I think we would be open to learning more about some of these applications where maybe an integrated SERS would provide value or use to someone. So if you have a very compelling application where integrating SERS would be helpful, please reach out and talk to us about it. We'd be very interested in learning.
So one of the questions is, I'll interpret more of a broad question, but if you have a SERS substrate like we're talking about, does that mean that you could potentially use a cheap spectrometer as opposed to a more expensive spectrometer?
That's a good question. I think that there's going to be some trade-offs with using a cheaper spectrometer. Arguably the most important is the actual resolution you may be getting. With Raman spectroscopy, you do want good resolution to resolve those different peaks. Again, for really complex molecules, that would be important. I will say I've run some initial tests. I had an intern this summer who was working with me on Raman spectroscopy, and we did use one of our CCS-based spectrometers, and we did find that you can still get a good Raman signal with our SERS substrate on that, let's call it a lower cost spectrometer. So it's definitely possible, but there's always going to be trade-offs you need to understand and account for in your system.
This one here, I'll take just to expand a little bit more. I think you talked a good bit about the shelf life. So the question is really the shelf life after delivery. How are the substrates shipped, and is there a vacuum inside the pill container? So the substrates themselves are put into the pill container. That pill container is loaded into the case, and then that's vacuum sealed before we ship them out. So the studies that we're talking about, currently, and and giving a time frame that we're talking about right now, that's really been since the development time frame. Tests that we're doing, are comparisons of having these substrates in ambient conditions obviously protected from dust or debris, but we're not storing them at chilled temperatures. We're not, there would be a typical office-like environment or lab-type setting, so room temperature and room humidity. So as far as, once you open that seal up, that's the type of testing we're doing right now, but we do ship them under vacuum, not then in the pill container, but the entire package itself is shipped under vacuum. As I talk, more come in, so I apologize, I'm going to catch up here. Okay, so I'm getting a lot of great comments, and I think what I would like to sort of piggyback off of those comments that are coming in is that Matt had just echoed this, but if you're working with SERS currently, and we'd love to learn more about those applications and the type of goals that you have. Thorlabs is a very collaborative, friendly environment. We love hearing about new applications, and we love seeing how we can help you in a very customer-centric way. So if we haven't answered those questions, if we haven't hit on some of the details specific to your application, please feel free to reach out to us, and we'd love to continue that dialogue. So I think this next one, Matt, I think I might be able to answer this too, since I was involved in some of that workup, but correct me if I'm wrong. So when you talked about the linearity study or some of the other signals that we measured, and we talk about those signal intensities, are we talking about just the peak height? Are we talking about peak to background? And I think I'll go a little bit farther than that. I think we evaluated under a couple scenarios. We found in many of these instances just integrating the area under the curve. So after you would perform a baseline correction to that Raman signal, effectively to remove any residual fluorescence that may exist or simply background signal of the measurement, at that point, defining a key or critical region around the analyte of interest and the feature, then integrating the area under that curve in order to generate the final intensity value that we use for comparison. Yeah, a general question here. Is it true that gold's appropriate for 785 and silver for 532? Could gold work as well under 532?
Yeah, great question. So I would say that gold for 785 and silver for 532 is a nice rule of thumb, but there are instances where maybe silver can work to some longer wavelengths or shorter wavelengths, same with gold. Gold, I will say, probably won't work very well at 532 just due to the plasmon resonance of gold dropping off shorter than that. But that's not to say if you had some molecules that were on just a bare piece of glass compared to gold, even at 532, I'm sure you'd get some signal enhancement, but it would not be anywhere near the levels we're getting.
So we have a couple minutes left here. I think, unless there's other ones, please feel free to submit them. But I think, one of the, last ones I see here that we really haven't answered in other discussions, hypothetical question, but, if someone were to take one of these substrates and then try to break it into smaller pieces, should there be concern about affecting the surface for the SERS substrate?
So I would say that there's definitely concern over affecting the surface substrate, but I would also say that if you're willing to try it, we'd be willing to learn and see, hey, there's a very efficient way to dice these even smaller once you have received this already small substrate. But what I would say is if you're looking for smaller pieces, let's say you want 1 millimeter by 1 millimeter, just reach out to us and we would be happy to work with you to see if that's a solution we can make in-house and make it more uniform and custom to your needs.
Okay, so I think one thing I will also say here is that if we have not answered your question, and I apologize because it's my job to make sure that these questions are being shared. If we have not been able to get to them right now, know that we will follow up with you, and we will answer that question if we did not have time to cover it here today. But I do believe that is all the time that we have today. So I'd like to thank Matt once again for his presentation. If you'd like to be notified about our future webinars, you can subscribe by clicking on the button below, or check on our website at www.thorlabs.com. www.thorlabs.com/webinars. Thank you very much for your attendance, and we hope to see you again.